Okay, so this just another example, but you already got the problem of the concept of page table. As far as the kernel is concerned, of course we must keep in its memory a list of busy frames that are allocated currently allocated to the page tables of the processes known to the system, and the free page. The free frame list. So that, well, you can select the first one in the list as the free frame to allocate one or more pages of a new process. For example, here you had this free frame list, 14, 13, 15, 20. 4 pages, logical pages are compose the new process. So page 0 will be given to, will be put in frame 14, 13 will get page 1, and so on. Nothing special. Implementation of page table. So as I said, the page table is kept in kernel memory, and the hardware needs a page table based register, one that indicated you what's missing, and also a limit register that tells you how many pages are included into in this process. As I said, in this scheme, every data instruction access requires 2 memory accesses, 100% of overhead. To solve this problem, the hardware is supplied with the so-called associative memory, or better, the translation look aside buffers. What is an associative memory? As a concept, an associative memory, normal memory, you access through an address, and you get the content. So if it is 10, you get 10, okay? An associative memory, instead, is like an hash table. It's like an hash table. In an hash table, you enter with the content, and you get the address where you find that content, the key. The key, then somewhere in the hash table you have the pair, key, and information, other information. Okay? Address. So I use this address to get the information. Okay, it's dual. Of course, this is a completely associative memory, and it can be implemented with some costly device, but for the purpose of the kernel instead, it is possible to use some modification of the concept of associative memory to use memory that is not expensive and to get essentially the same advantages of the associative memory. What is this translation look-aside buffer? As I said, the associative memory is like this, and we could use an associative memory to associate as a key the page and as information the frame. Okay, but in this case, we must have a mechanism that, of course, doesn't look at every line of this associative memory to get the page and the frame association. Of course, it must be this must be done in parallel by hardware and fast enough. So, in the TLB, the trick is this. So, logical is an associative memory. Practically, it is implemented in this way. If you look for page P, you look at a specific location of the TLB, not at every possible entry. So, to be more specific, this TLB typically are lower dimension, of course, memory, 64 kilobyte, 256, or something like this. And you have several entries, okay? But again, due to the locality of references, okay, if you look for this location, you will find P and frame, okay? So, of course, since the number of these lines is small with respect to the pages that you can keep in memory, this TLB in the long run, in the short run also, will be filled by entries, okay? So you have to replace some of these entries. But if you use P will always go here, okay? Maybe with an hash table, okay? So when you look for P, you don't look at every possible entries, but just one entry. Or from an engineering point of view, it is better to have this TLB doubled or 4 times. So if you don't find it here, you can find it here. So P, you can look for P here also, okay? So it's like an hash table. You look at the first TLB, if there is not, you go to the second, and maybe in some system you have 4 of them. So remember that this is faster than main memory. So the scheme for the implementation of page table is illustrated here. So you have the page table in kernel memory and TLB, of course, in kernel memory, and logically you compare P with all these entries. As I said, it's like an hash table, so if you are looking for P, maybe you look here. If you find P here, you immediately find the frame, and you add the displacement and arrive here. What is the key point? That this is much faster than main memory. So it's more expensive, faster, with a different technology. And in this case, we have a TLB hint. So the page was in the TLB. So the TLB is a shortcut that allows us to avoid going on the TLB, okay? Because of course it keeps some entries of the global TLB. So suppose that this page table is maybe very large if you have a huge program. Only part of them are kept in the TLB. Typically the list recently used. So the strategy when this is full, completely filled, is to replace the oldest frame, so the one that is list recently used. Okay, so by hardware, the translation is done in this way. Check if the page is here, the key is here, and get immediately the frame number. Otherwise, you have overhead because you have master read. This update the TLB and read the offset here. So in this case we have the TLB miss. So this scheme works due to the locality of references, because when I do a reference to page 4, the probability that I make another reference to an address in page 4 is high. Okay? Okay, we can compute the effective address time if you consider that you have this time epsilon for the TLB and for memory larger key, we can fix an hit ratio, a probability of success of a hit. So in case of success with this probability, the effective address time will be T, so epsilon, the TLB, plus T for accessing the data. Otherwise, with probability 1 minus alpha, you have 2 times T, because you must read the page table and value, plus the update of TLB. Well, with some values here, it's not important. What is important here is that you get this information. So the effective access time grows by 22%, okay, with these numbers. And here we use the probability, I don't remember the probability, okay, 98%, that is reasonable. Normally you may have even more. Nevertheless, 22%, and so you may say, well, there is an important overhead, but it is so important and so nice, the paging mechanism, that we accept this speed reduction, this access time increase, because we have a lot of advantages. Okay, memory protection. The paging mechanism allows us also to add in the page table some information. The simplest information is a validity bit that tells, this is used mostly for virtual memory, we will see. But imagine that this is the page table of this process, and pages 6 and 7 are marked invalid. What does it mean invalid? Data are not in main memory, so there is not frame associated here, and the bit is invalid. We can use this bit also for detection, so to identify a page as read-only, for example, or read-write. Okay. In this way, immediately by hardware, we can check if we are doing an operation that is allowed or not for that instruction, typically, or for some data. With paging also, we can share pages among processes, because it is enough that the two page tables of two different processes point to the same physical frame. It's not so easy, but you got the idea. So, for example, if you have an editor running, okay, the code pages of the editor may be shared, while the data needs to be local for each process. So, in this case, the kernel must avoid to allocate 2 times the code pages of the editor, but it needs to allocate a page for data 1 and data 3. It's not so nice because the editor is compiled, is pre-compiled. Okay, so this data 1 and data 3 must go on page 3, both. Otherwise, it doesn't work. Okay. By the way, this is how we can have a shared vision, even in Unix. Now, a step forward. Structure of the page table. Hierarchical page tables. How many pages we have with, said, with 1 kilobyte pages dimension? It would be 22 bits, so 4 mega pages. Okay, what does it mean? That the page table would be big. Okay, so for a large program, you may have a huge page table. Okay, so to avoid this, we can use the 2-level page table in this way. So this is again useful for virtual memory, but suppose that you have this scheme where you have a directory table or outer page table. Okay, it's called directory table in the Intel terminology, and every entry of this table refers to a page table. Sorry, a piece of a page table. So this goes from 1 to 500 and so on. Okay. So the page table is split into this first level and the second level. So here you have 200% of overhead with this scheme. In this way, what happens in virtual memory is that we keep in main memory the directory table, and we load from the disk the part of the page table that is used at that moment. Okay. So for this scheme, you may have a subdivision of the bits for the logical address in this way, for example, for 1 kilobyte pages with 10 bits. Then you can use a declaratory table that contains that has 4 kilo entries, and the page blocks are again of 1 kilobyte. As I said, in this architecture that is used by Intel, by the way, as we will see, with 12 here. The overhead, as I said, is 200%, because to reach this byte, you have to read this frame, and finally this offset here. Of course, the trick again is to use a TLD. What do we put in TLD? The K part and the left part. What you put? First we put P, okay, here. So here you have a P and frame, page number and frame. Now what we put in the left part? Which page? Both P1 and P2. So this part, this is the key. So this 22 bits will be the key, because what you want is a shortcut to F. So you will have in the TLB as a key the concatenation of these two sequence of bits. So P1 and P2, and of course the frame. So you will have a shortcut here, from here directly to here. Okay? Exactly in the same way. So for 64 bit architecture, you may have something like this, two-level and three-level paging schemes with 4 kilobytes pages, for example. You may have a lot of pages here, or even like in Unix, something like this. 3-level, 300%, and TLD keeps all these bits as key. Well, the other possibility is to use hashed page tables, but for inverted page table, I have no time to, and it's not really related to operating systems. Segmentation, yes.
But I recall from the operating system course that there was a memory allocation technique that is like in an array of 12 has 10 direct pointers, then one indirect.
No, this is for the allocation on the disk. We will see. This is for the block on the disk. Here we are talking about the main memory. So, the second concept of memory management is segmentation. So we have paging and segmentation, which is the main difference between paging and segmentation. Paging is used essentially for efficiency, for allocation in memory. because it's like having small tiles, and having small tiles, we can cover all the memory without leaving a lot of holes, like in continuous memory, okay? So, page is characterized by fixed dimension, okay? Fixed dimension, and doesn't carry any, say, characteristics, while a segment, on the contrary, is a variable dimension object that okay, is meaningful, while a page is not meaningful because you can cut the program when the 4 kilobytes end or 1 kilobyte ends, okay? So without any notion about routines, functions, stack, whatever. A segment instead is a unit of protection in particular, because it's meaningful. So a segment may be a main program, a function, a method, an object, maybe a region of data with a global variable or local variable, stack, etc. So the main difference is that while we can protect pages, as I said, read and write, for example, or execute, with pages it's difficult because maybe you have a boundary with different possibility of rotation, okay? While with segmentation, each segment is defined by the, say, read executable here, you cannot change the code, okay? While stacking do read write and not executable, something like this, okay? So the concept of segmentation is a way of partitioning in a meaningful way a program, okay? An application. So the same strategy that I introduced for paging can be used for paging with a segment table, okay? But the problem is that the segment have a variable dimension, so you can spread segments of a program around memory, but the fragmentation is much more evident in this case, because you cannot simply fill the first frame that is free. You need to fill contiguous memory for segment number 3. Of course, you have the segment page table, etc., like for paging, with the additional problem of having different dimension for the segment. But as a matter of fact, what we get at the end is segmentation plus paging. So each segment is divided into pages. So the segment is the unit of protection. Each segment is divided into pages, so that the segment can be spread around the memory. So in this case, we have both a segmentation mechanism and a paging mechanism that can be activated even independently. In the Intel, it is possible to work with segments and without paging. if you want to use paging, you have to prepare the page table for each segment and then activate the paging mechanism. Okay, so say the memory management unit that since this point you can you have to use paging. So the generated addresses have to be interpreted with the page table. So, as said here, an Intel Pentium architecture supports both segmentation and segmentation plus paging. The CPU, as usual, generates logically addresses, and the segmentation unit generates what in the Intel terminology is called the linear address. It can be used directly as a physical address, or can be passed to the paging unit, which generates the physical addresses through the page table. For 32-bit architecture, the number of the dimension of a page is 4 kilobytes, and it uses a two-level hierarchical subdivision of the page table with the directory page table, 10 bits. 10 bits means 1 kilobyte divided by 4, it means 256 entries. And the second level, there are 256 entries of 4 bytes. So you have 1 million possible pages. It's large enough. Well, segmentation in the Pentium architecture is applied to every access. So the logical address is seen as a field that is called the selector, and then the offset. So every object in the Intel architecture is accessed through this segment descriptor table. What is a segment? For example, the interrupt table is accessed to the segment descriptor. The kernel memory is addressed as a segment or many segments, and the same is for the users. So this is for protection. Everything is passed through this segment descriptors. We will see in detail, more detail later on. So, as I said, we have a special register, CR3, that points to the initial entry of the page directory. Then we use this 10 bytes for 10 bits for as an offset in the page directory, and the second 10 bits are the offset in the page table. So, because this offset we arrive here. From here we take the initial entry of the page table, and finally we go in the 4 kilobytes page table. It's possible to change the granularity, so-called granularity of the page, of paging, but normally we have this kind of granularity. Otherwise, changing 1 bit, the pages are considered of 4 megabytes. Setting this CR3 means that we have already prepared this structure, and so it means that we are sure that we can activate the memory management unit. It's a little bit dangerous, but okay. As I said, the linear addressing units may take 4 fields rather than 3, and of course it has to rely heavily on the TLB translation mechanism. Virtual memory now. I will leave something for the future because in the laboratory I want you to use memory mapping, so I will explain memory mapping. Okay, virtual memory is based on the concept of paging on demand. What is paging on demand? It means that initially the kernel loads only a few pages of a process, not the entire image. Okay? Why? Because of the concept of a residence set. So each program has in time what is called the residence set. So a number of pages that are enough to allow the process to proceed without what? Without failing to find a page in memory that is needed. So if you put a single page initially, of course, as far as you work on this page, it's okay. But what happens when you make a reference to some data that is not loaded in memory, or the next instruction makes reference, is a jump to something that is not in memory? Okay? So here, enter to the play the paging on demand. So, and the concept of page fault. What is a page fault? Among the interrupts and exceptions that drive the kernel, you know, the interrupts are asynchronous event. You hit a key and this generates one interrupt. The clock generates an interrupt when some time has expired. If you divide it by 0, this generates an exception, an interrupt that is taken by the kernel, and so on. If you violate the domain, this generates a trap. Everything is managed by the kernel. In particular, what we have, what is important today is the concept of page fault. Page fault means that a reference is done by a program to an address whose page is not in memory currently. So this would abort, of course, the process, but the kernel recognizes this kind of exception or interrupt and understands that it must find absolutely a free frame in memory where to load the requested page. when the page has been transferred from the disk, from the backing store, the instruction may restart exactly at the same point where the page fault was generated. This is the main difference between all the other interrupts and page fault. The interrupts, let me conclude, so probably you understand. When you receive an interrupt, the return from interrupt makes you go to the next instruction, okay? For the page fault instead, when the kernel has loaded in memory the missing page, the process that was blocked because restarts from the same instruction and this time finds, so doesn't generate page fault, please.
So the kernel used the trace of the process to do this.
The trace. The kernel recognizes from the number of this interrupt, page fault, that this is not an error, but a request from service, of service. So it knows that it has to load from the backing store in memory the missing page. So the memory paging and the paging on demand implement the virtual memory because we can run a lot of processes, each of them using few pages. Few, depends on the reasons, but not the complete image. When a page is missing for one of these processes, the kernel this generates a page fault and the kernel brings in memory the missing page. Of course, in the long run, the page will be full. So the kernel has to select also a victim to replace the page that is immediately needed with a strategy. We will see the strategy, but not today. Okay, so let us go on. Okay, virtual memory. Only part of the program needs to be memory for execution. The logical address space in a system that implements virtual memory with paging on demand can be huge. So as large as essentially the backing store. Okay? Because it has to put somewhere the pages. Virtual memory also allows space to be shared by several processes and allows to more efficient process creation. When we create a process, we don't need to copy all the data, but just the part that are needed for running the process for what is called a warm start. Of course, we concentrate on demand, paging on demand, but the concept is the same for segmentation on demand. So here you see a layout of main memory and background disk. This represents the disk, backing store. So suppose that you have in memory some pages. Each page, of course, is mapped by the page table in physical memory. And for a process, it is not necessary that the complete page table, okay, is mapped on physical memory. Only few pages can be mapped there. So, for example, suppose that this one of these pages is instead in the backing store. Okay, so when we run, for example, in this page, this page, but on this page, this is mapped on memory, and there is no page fault. But if this one of the instructions inside this page make a reference to data, or try to jump or to call an address in this page, the bit here will be invalid. So there is no mapping. This generates a page fault. At this point, this process will be blocked with high priority, and it has to wait until the kernel finds the page that is referring, for example, say this one, and finds a hole here in memory where to transfer this page. This takes some time, of course, because the disk is not fast. And after this time, this process becomes again ready, and probably with high priority restart the instruction. Okay, for in this figure you see also why it is important to do also paging for all the kind of segments that we have, because this is typically the snapshot of the memory for a process. You have the code, the global data, the heap for the malloc operation, and the stack that proceeds in opposite direction. You can exhaust also the virtual memory. If you allocate huge matrices, for example, you can also exhaust the virtual memory, because your swap file is not large enough. Okay, shared pages, no problem. Okay, so demand paging. Demand paging, I already explained it, but imagine that you want to swap in and swap out a complete image. This figure illustrates what is done. Okay. Simply, the kernel keeps the list of empty pages and transfer on demand the pages that are missing. If the free list is empty, it has to find one page, at least one page for replacement. And this is done through some strategy. Okay, then the invalid bit, I already illustrated it. So, in this case, you have A, C, and F that are in memory, so you have only 3 entries, and the related association between page number and frame number. The pages are in the backing store. So A, C, F are in the backing store. And if you need to use, say, page D, it has to be placed somewhere here, so that the page table are updated with valid as I said, that if everything is filled, maybe by the basis of other processes, the kernel decides, for example, that this page is the victim, which is the rationale for the kernel, is to minimize the traffic of the disk. So, if this page, for example, has not been changed, no one wrote on this page, it is not necessary to copy it back. So this is one of the criteria for selecting and editing. Page fault. So page fault is illustrated here with all the steps. So you have a page, and somewhere in the page there is the instruction load M. And M is an address on this page, different from the current page. And this page is invalid. Okay? This generates a page fault by hardware. Okay? This trap is managed by the kernel. What happens at this point that the process that did this loadM is put on the blocked state, and another process may run. Okay? The kernel prepares the transfer of the missing page, this page where M is located, into a free frame. To do this, it follows its strategy, and transfer this using DMA block in parallel with another running process. When the transfer is completed, it updates the page table of this process and restart loadM. Since in the Intel architecture there are indirect and indexed references, you may have up to 6 page faults for a single instruction, because I don't find it always restarts from the beginning, okay, and find, of course, what was missing in the previous page fault. The duty also of memory management of the kernel is to keep low the number of page faults. Example, if you have a program, okay, and you are doing your thesis, and you want to run 20 copies of this program with different arguments, okay, and say, well, I run 20 copies of it. What probably you get is that no one of them run as you expected, because they generate a lot of page fault. This is called a situation of thrashing, where each instruction generates a new fault, okay, or every few instructions generate a fault. So you must be aware that multi-programming must be always controlled, otherwise you see only the light of the disk flashing and nothing going on. Okay, so performance, as we did with the cache memory and the buffer cache, the performance of the demanded paging depends on the frequency of page fault. Okay, because if you don't have page fault, you run at the speed of memory, of the cache memory. Otherwise, in case of miss, it's much slower, because with this probability of page fault, you need to swap out one page probably, and swap in another, and restart the instruction. These 2 times are much more than the memory access times, because you have the delay for the transfer and the queue, even for the normal file system. So again, a small example. We imagine to have this kind of times, 200 nanoseconds for an old memory, access time 8 milliseconds, not too old for the disk. So the effective address time would be like this. Okay, so you see that the probability of page fault, so the number of page fault, the frequency of page fault, must be very low. Otherwise, the effective address time becomes enormous. Okay, so that's why the kernel, but also yourself, tries to avoid excessive multiprogramming. So keeping, maybe you can submit your job, but the are kept in a state of submission, because there is not enough resources, or there are too many page faults. Okay, so if you have a page fault of frequency of 1,000, 1/1000, it will increase the access time to memory 40 times. That would be enormous. But again, normally you don't have this problem. So now, finally, I rather than later, I talk about mapped file now, because we need for the laboratory. Mapped files. Okay, memory mapped files is an important concept. So in this course is system and device programming, but as I said, we look at internals of the kernel, but we are interested on a good usage of the system calls. What is memory map? Memory maps allows you to, as the name says, to map in memory a file. So this allows you, rather than to read with read and write, to access the content of the file like an array. Okay? Much easier. So you see your file content, as an array. So if your file, a binary file, it contains structures, records, so a person, information, name, surname, age, etc. Okay, you will, after mapping it on memory, you can use it as, say, if you map on array A of 0, A of 1, A of 90, okay? Like an array. Of course, the file must not be enormous, because it uses virtual memory, as a matter of fact. It is nice because in a transparent way uses only the memory that is necessary, because normally you process a file sequentially. So initially the last part of the file is not in memory, etc. Okay, so it uses virtual memory to map a file to in memory. So what which is the system call is mmap that takes a file descriptor, of course. So you open a file and you can map from the beginning, normally using 0, or you may map from an offset. Then here you can use an address or null, because it's like a malloc. This system call will return an address where the file is mapped. Okay? Then you pass the size for the file, and then the protection, read, write, or exec. And here you have also some flags that normally is not used for you, because no, yes, it's used because there are a lot on Linux, but essentially you use map share when you want to work with several threads on a file. So immediately I show you the example. Quit here, Control P, CD, System&DeviceProgramming, CD method somewhere. No, where is this method? Okay, there, method 5. CD, method 5. Okay, let me open SDP, method 5. Okay, map to C. Okay, you have to use some includes for the mapped file, but essentially here I create a file, a long file, but just writing at the end. In this program, I put at the beginning of a page just a character, so it generates a page fault for every write that it does. So, open the file. This system call allows me to take the length of the file, fstat. In this program, I force the length to be page aligned, but it's not necessary. mmap does the job for you internally. And here is the trick. So, read write, map shared, fd, the file descriptor, from offset 0, and len, the length of the file, and here I put null, so I get the address that it decide to give me. So of course this is of this type. I can cast to the appropriate type if I know that my binary file here contains int number, it will cast to int. If it contains structures, it will cast to particular structure. Then, for 10 times in this case, I print loop and look here from I equals 0 to len minus page dimension in a step of 2 pages. So for every even page here, 0, 2, 4, etc. I take the content, current content of the file. See how? Simply, as an array. I don't do any read. System call. Exactly like an array after mapping. And then I put a y, okay, inside on this location and on the next byte. So this generates, of course, a page fault probably because the pages not be loaded. And then I do the same thing on the odd pages, starting from page and increasing by multiplying by 2. What is interesting running this program is that with total dump, since it's shared, with total dump and debugging this program, I can see that my file is modified every time I do this operation. Okay, so it doesn't wait to update the file. What I do in this array is done on the file in a way that is completely transparent to me. So in laboratory you will have to do some quick sort, and of course rather than operating on a file, you first map the file and then work as if it were an array. Okay? Okay. Well, sorry to be always fast, but this